welcome everyone. Today we're very pleased to welcome Luke Barnard. Luke is a postdoctoral research fellow at the University of Reading, and Luke's expertise centers on the propagation of coronal mass ejections and their impacts here at Earth. His excellent quality of research is exemplified by a number of high-impact scientific publications that have been cited more than 900 times. Luke is also a member of the Citizen Science Solar Stormwatch project, and he's contributed significantly to the construction and exploitation of this novel dataset. So today, Luke is going to be speaking on coronal mass ejection modeling and prediction with heliospheric imagers. So I'll hand it over to you, Luke.
Thank you for the introduction, Jasmine. So yes, I'm Luke, and I'm going to talk to you about coronal mass ejection modeling and prediction with heliospheric imagers. Before we get started, I'd like to give thanks to my colleagues and mentors, Matt Owens, Chris Scott, and Mike Lockwood at University of Reading, and then also Kurt de Koning out in Boulder at SWPC and CIRES. So, the bulk of my research centers around how can we use heliospheric imagers to improve coronal mass ejection forecasting. So this animation is a schematic that tries to kind of summarize that problem. So the colored contours show a CME erupting out into the solar wind. You can see the CME here. And the question is, if we have white light observations of this CME erupting into the solar wind from one or more vantage points, how can we use those data with any kind of model to improve the representation of the CME as it flows through the heliosphere and the prediction of its properties at Earth? So to begin, let's think about what CMEs are to start with. So this movie on the left-hand side shows an EUV image of the solar disk, and the outer image is a white light coronagraph. These are data from, I believe it was stereo A. And this movie lasts 29 hours, and what you can see over that period is a sequence of eruptions. I think I see about 5 CMEs being launched. So CMEs are impulsive eruptions of magnetized plasma from the sun's corona. So you'll see the formation of structures that, if you look down here, there's one coming fairly soon. Oh, there we go. What you're seeing there is a load of structured magnetic fields and mass, which are being released out through the corona into the heliosphere. And more often than not, what we're talking about when we think about CMEs are magnetic flux ropes or magnetic clouds. And so this schematic on the right-hand side shows how a CME magnetic cloud might look like as it's embedded in the Parker spiral solar wind magnetic field. So you've got this twisted magnetic structure which is linked with 2-foot points at the sun, and it propagates out into the heliosphere, deforming the solar wind magnetic field as it goes and gets draped over the front. And if this CME travels fast enough, then it can also generate a shock wave that also propagates ahead of the CME through the solar wind. And so this is a view close to the sun. But if we take a look back at a different version of that earlier schematic, after the CME leaves the corona, it propagates out through the solar wind, where it interacts with kind of the dynamic structure in the solar wind. So this is a snapshot from a model, but these are also heliospheric imager observations of the same CME taken from 2 vantage points. So stereo B was over here and is shown in this plot, and stereo A is here and shown in this plot. And so there's an awful lot of structure in these videos. You can see that CMEs are incredibly dynamic, and there's a lot going on. So there are many good reasons to study coronal mass ejections. From a more physics perspective, they are very important in the progression of the solar magnetic activity cycle, as CMEs drag out magnetic flux from the corona into the heliosphere. It plays an important role in the evolution of the sun's magnetic field. But I'm more interested in coronal mass ejections from a space weather perspective. So when CMEs propagate out through the solar wind and eventually reach Earth, the magnetic field structure of the CME interacts strongly with Earth's magnetic field and can drive the strongest geomagnetic storms. The most extreme geomagnetic storms are, as far as I am aware, exclusively driven by energetic coronal mass ejections. And that kind of sequence of activity of a CME reaching Earth and driving strong geomagnetic activity has a chain of impacts throughout the atmosphere and on the ground. And so this is an ESA diagram that tries to highlight some of those things. But it's also important to note that coronal mass ejections have strong impacts on other space weather effects. So for example, the shock waves that they can drive in the corona and low heliosphere are very important for the generation and propagation of solar energetic protons. And the plasma environment of CMEs is also important in the modulation of cosmic rays. And so actually CMEs are generally important to most of the space weather impacts that we observe at Earth, I think. But in terms of kind of trying to quantify what those impacts are, so you could look at some of the modeling work that's been done. So back in 2019, Edward Orton did a modeling study of the economic impacts of extreme space weather to the UK's critical infrastructure. And what they found is if there was no space weather forecasting, they reckon an extreme event, somewhat like the Carrington event, would cost of the order of £16 billion. With the current forecasting capability, they reckon that cost would be around £3 billion. But they also argue that if we could improve our forecasting capability, maybe with a dedicated solar wind and space weather monitoring craft at L5, we could improve our forecasting capabilities and reduce that cost to around £1 billion. And so, I mean, cost shouldn't be the only consideration on these things, but it does highlight that space weather forecasting is understood to have value, and that actually, if we could do it better, it would have more value. But there's also a lot of focus on extreme events. But I think Carol Shriver made a very good point back in 2015 that it's probably important not to just focus on extreme events, and that if you consider the integrated cost of more moderate but more frequent space weather events, that is very likely comparable to the integrated cost of the less frequent but more extreme events over a suitable time base. In terms of space weather events, space weather effects, I'm not really going to talk about them anymore, but I can recommend that you go and watch Jim Wild's MIST seminar on space weather impacts that he did earlier last year. So moving on, as I said before, I am mostly interested in using heliospheric imager data, and particularly I focus on using the heliospheric images on the stereo spacecraft. So stereo was a mission that was launched in 2006. They were twin satellites that were both put into Earth-like orbits. Stereo A drifted ahead of the Earth and Stereo B drifted behind. This animation on the right-hand side shows how their orbits have evolved from early 2007 until last week. Unfortunately, in 2014, we lost Stereo B, but on each of the stereo spacecraft, there was the SECI remote sensing package. So SECI was the Sun-Earth Connection Coronal Heliospheric Investigation, and it consisted of an EUV imager, an inner coronagraph, core 1, an outer coronagraph, core 2, and then an inner heliospheric imager, HI1, and an outer heliospheric imager, HI2. So that very first movie I showed you of the CMEs was from this EUV and core 1 field of view. And so this is actually a simulation of the expected fields of view of the images. This shows how the scale of the HI1 and HI2 fields of view compares to that very, very narrow.
So they're different.
Pardon, sorry?
Sorry, someone just wasn't on mute. Carry on, please.
So the scale of the HI1 and HI2 fields of view is vast compared to the coronagraphs, really. And so HI1 has a 20-degree field of view, which is centered 14 degrees away from the sun, and HI2 is a 70-degree field of view, which is about 54 degrees off the sun. So this is an early image from the HI1 and HI2 cameras back in 2007. You can see Venus here, you can see Mercury here. The background star field is very bright in these images. So this is from stereo A. So the sun is off to the right-hand side, and Earth and the moon were around about here at that time. But so the question is, how do we actually observe heliospheric and solar wind plasma and CME plasma with heliospheric imagers? So this is a diagram that tries to show how we get how we observe light scattered by solar wind and CME plasma. And so that happens via Thompson scattering. So Thompson scattering is the low energy elastic scattering of photons or light off of free electrons. And so if we have an observer over here and we have the sun over here, what you'll find is, and a scattering site here, which is just a free electron or a blob of electrons. Light will come down here and is Thompson scattered down to the observer here. But Thompson scattering depends on the scattering angle, and so the scattered power changes with the scattering angle. More photons are forward and back scattered, and scattering is minimized perpendicular to the incident light. And so this is kind of explained by this differential cross section here, which describes how the power is scattered into a unit of solid angle, and that it depends on this scattering angle chi. To try and visualize that a bit better, if we have a stream of photons coming in from the right-hand side and scattering off an electron in the middle here, they're scattered off in roughly this distribution like this. So you can see there's a preference for forward and back scatter, and less are scattered perpendicular to the incident light vector. Well, if you fold together the details of the Thompson scattering with the illumination of the plasma, what you find is that the sensitivity of a heliospheric imager to a specific blob of plasma changes depending on the location of that plasma. And so this forms what is known as the Thompson Plateau. So this plot here shows contours of a normalized sensitivity to basically the same package of electrons being dumped somewhere. And so if you look along a given line of sight, what you see is there's quite a broad region where you get a similar sensitivity to the same package. And what this means is it's you get similar signals for elements of plasma that are propagating with quite different exit angles from the sun. And it is one of the reasons why it can be quite tricky to do photometry with heliospheric imagers. The wide angle nature of it means that actually the brightness profile doesn't very well localize where that package of plasma is in space. And so what we tend to do is use difference images to look at the location of features in the HI field of view. So rather than looking and kind of doing photometry on these images, we will isolate the front of the CME and use the time elongation profile of that CME to describe it. So elongation is a angular radial coordinate, and position angle describes kind of your rotation from solar north. Sorry, I didn't mean to move on there. So for the rest of this talk, I'll be discussing the evolution of CMEs in the heliospheric imager field of view in terms of their time elongation profiles. And so this difference imaging also helps deal with the fact that the star field is very bright in the heliospheric imager field's view. So there are two classes of model that are typically used to analyze CME propagation with heliospheric imager data. And these are geometric models where you prescribe a simple geometric shape to the CME structure, and you assume that you are viewing the tangent of that with the elongation profile. These are simple to implement. They've got very few degrees of freedom. And what's common to do is you use the geometric models to estimate the CME's kinematics low in the heliosphere, and then you use something like a drag model to extrapolate those kinematics out to Earth to see when the CME might arrive and what its speed will be. Or alternatively, there are numerical models. These are a bit more complex. They are much more computationally expensive than the geometric models, but they do offer more detail. And comparison with the HI data is a little trickier. So I'm going to talk about both of these in turn, but we're going to start with the geometric models. But to work with the geometric models, I am actually going to have to use a numerical model. And so I just want to introduce a numerical model that we've been developing and using at Reading. It's the HUXt model, the heliospheric upwind extrapolation with time dependence. This is a reduced physics heliospheric model where it's a time-dependent radial solar wind, and it's based on the solution of Berger's equation, which means it's an incompressible hydrodynamic flow. And although that sounds like a very severe approximation, what you find is that if you compare this with a 3D MHD solar wind, such as Heliomass, it actually reproduces the solar wind speed profiles to within a few percent. And you can include CMEs using cone CME parameterization, just like you would in Enlil, where CMEs are essentially injected as a velocity perturbation at the inner boundary. The advantage of HUXt, and why it's very useful for the work I'm doing here, is that it's very efficient to run. So yeah, 5-day run in the ecliptic plane takes less than a second. And for the work I'm going to show, I need to do hundreds and thousands of runs at times, which just isn't practical with some of the more advanced 3D MHD models like Enlil or Euphoria. This work was published last year by Owens et al. In Solar Physics, and the model is open source and available on GitHub if anybody wants to have a play with it. So with these geometric models, as I said, you prescribe a simple geometric shape and interpret the observed elongation profiles in terms of that. So this shows the 4 commonly used models. The first one was fixed phi, where you essentially assume that you're seeing a point source. And so your elongation profile corresponds directly to this. In the next, it was the harmonic mean method, where you assume you have a circle which is expanding with one edge anchored at sun center, and the rest of the circle expands self-similarly with a half width of 45 degrees. And so what you're seeing here is that as we observe this tangent of the CME, that gives you a relation to the actual apex of the CME. Next was the self-similar expansion model, where we say, okay, maybe it's a circle that expands self-similarly from the sun, but one edge isn't anchored. And then, so that adds another free parameter, which is the half width of the CME. And then the final version is the ellipse evolution method. Unfortunately, the tangents didn't render, where you assume that the CME is an ellipse and you observe the tangent of that ellipse, and that adds another free parameter, which is the ratio, the aspect ratio of the ellipse. And just to highlight the point that if you put all these models with the same radial apex distance, you observe different elongations for them. But you can use these models to estimate the kinematics of the CME's apex from the time elongation profile observed in a heliospheric imager. And there's a large body of work that's been built up doing this. And this just shows a few examples from Mishra et al., Moser et al., and Rollet et al. So for example, what was common is that you would convert that time elongation profile into a time distance profile of the CME apex for the different geometric models. And then if you differentiate this, you get the speed profile. But when we started playing with this work 5 years ago, what we found is that we couldn't understand why the errors were so small on the observed distance profiles. And we also didn't understand these unphysical late stage accelerations that you see in the speed profiles, for example, in this plot here, but also here. So we set about trying to understand what the errors are if you do this process and how well it works. And so one issue that we thought is that perhaps the errors on the elongation profiles were being underestimated, because essentially most of these profiles are done by one professional researcher sat down manually identifying the profiles. And then we also thought perhaps it was the assumptions of these models breaking down, that you've got this shape which isn't interacting with the structured solar wind at all. So first things first, we worked with Solar Storm Watch to come up with a more robust estimate of the evolution of the CME front. So with Solar Storm Watch, we did a frame by frame tracking of the CMEs in different images. And by collecting, I believe it was around 10 classifications per frame, we were able to do statistical analysis on all of those identifications to come up with a robust estimate of the location of the CME front, but also the uncertainty on that. And if you do another statistical analysis that compares the CME fronts that you get from Solar Storm Watch with ones that we were able to generate ourselves through manual tracking or through ones published by other authors, what you find is that the Solar Storm Watch tracks are a more robust estimate of the CME front that tracks features more stably. And so when we tried to estimate the kinematics of these CME fronts using those same geometric methods, but with a good estimate of the uncertainty on the elongation profile, and also good estimates of the uncertainty in the CME parameters derived from coronagraph fits, what we found is that actually the uncertainties were very large and that you couldn't reasonably discriminate between the different models given their uncertainties. And worse than that, you couldn't easily make stereo A and stereo B agree with each other. But these models are supposed to be independent of viewing geometry. It's not supposed to matter where you look at the CME from, just that you're observing the tangent. And so the fact that you're getting inconsistent kinematics, as shown here from the CME speeds in stereo A or stereo B, was concerning to us. And so our early conclusion was that the errors are large. It's difficult to distinguish between the different geometric models, and that actually there is a good chance that the assumptions of the models are being routinely invalidated by solar wind structure, because that would explain this discrepancy between the results you get from stereo A and stereo B. But there was a big limitation to our work, which was that unfortunately at that time we only had 4 CMEs that we were able to study with the Solar Storm Watch data, because it took time to get those data together. And so what I've been doing recently is seeing if we can use simulations to test this. So the idea is that we can use a model like HUXt to generate CMEs. We can simulate what the observed tangent elongation profile would be from different observers at L4 and L5. and then we can compute what the kinematics would be from those geometric models applied to the simulated elongation profiles. And so first off, we'll do this for, sorry, the mute button is right over the play button. There we go. We'll do this for a fast and fairly wide CME injected into uniform solar wind. And what you find is actually, in this case, the agreement between A and B is good. For each geometric model, which are shown by the regular shapes here, and the HUXt CME is shown in orange, and the fixed phi is shown by the star, because obviously that's just a point. From each viewer's perspective, the models do a good job. If you then compute the apex distance and the velocity profile for HUXt in black, and then each of the geometric models in the colored dashed and dotted lines, they're in close agreement. The radial profiles look like they're basically degenerate, and the speed profiles are close to each other, barring a little bit of numerical noise. But it's not a good assumption that the solar wind is uniform. So we can repeat the experiment using structured solar wind. So this is the solution for Carrington rotation 2071 in June 08, where we put exactly the same CME in. All we've changed is the solar wind boundary conditions. And in this case, what you see is that this westward flank starts to lead the eastward flank because there was a small fast stream that was coming out through this way. And so actually, in this instance, you end up with a large disagreement between an observer A and an observer B, and a large disagreement between the modeled flank location and the geometrically modeled flank location, which is different for both A and B. Sorry, L4 and L5. But again, we can go back and compute the kinematics of these profiles for the L5 observer and the L4 observer. And again, what we find now is that after we've added in solar wind structure, although the kinematics profiles of each geometric model are pretty much degenerate with each other, they are systematically different for different observers. And you get this weird, seemingly unphysical lift up in the speed for the L4 observer. And this kind of highlights our point that it's not supposed to matter where you use these geometric models with an observer. And if your prediction is dependent on where the observer is, that is a problem. But again, this is just one case study. I'm sorry, just to highlight that point, if we now just compare the geometric models for, so this is fixed phi for the two observers, harmonic mean, self-similar expansion, and elliptical, what you find is that as this flank starts to lead, this becomes the tangent that the nearer the L4 observes, and because all of a sudden it starts tracking this flank rather than further down, the elongation starts to move more quickly, which is what gives you that speed enhancement. It's got nothing to do with a CME acceleration or any bulk change in the CME. It's that there's a fast stream affecting this flank of the CME. But as I said, that's just one case study. It's not terribly instructive on its own. And so what I chose to do instead was to rerun that experiment using the same fast and fairly wide CME, but I inject it into 100 different background solar wind structures. And then we're going to compute the arrival time error at 0.4 AU. And the reason we're going to do that is because that's roughly the heliocentric distance where the other extrapolation methods would be used to propagate the CME out to Earth. And what you do when you do that is, sorry, what you find when you do that is that the error distributions are basically degenerate between each of the different models, because with this viewing geometry, low down in the heliosphere, there's very, very little difference in the results you get from each of the models. But the error distribution is heavily biased to early arrivals. The geometric models arrive early at 0.4 AU. And this is only due to solar wind structure, because we know everything else about the model CMEs. But it's easy to understand that, because as I said before, if you have a fast stream, well, any difference in the CME, sorry, the background solar wind speed over the angular width of the CME, it will drag out one flank relative to the other. As you can see, there's the eastward flank is dragged out here and the westward flank is dragged out here. And what that does is pull the geometric models forward relative to the true CME apex. And so for these reasons, this is a limitation to how well the geometric models can possibly perform without including solar wind structure into them. And just one final point on this, I've focused on an L5 observer here because obviously there's much talk about having an operational L5 mission with a heliospheric imager there, so it seemed relevant. But these results do depend on where the observer is. So if we change the longitude of the observer from 20 degrees behind Earth to 90 degrees behind Earth here, what we find is that actually the error distribution evolves, and it's not until we get to around 50 degrees behind Earth that the geometric models only predict an early arrival at 0.4 AU. So I don't have much more to say on geometric modeling other than the fact I think there are quite severe limitations to how well it can possibly perform. But I also think there are other things we can do that might be more successful. So this brings us on to ensemble modeling. Ensemble modeling can be used to quantify uncertainty in forecasts using an ensemble of model runs. So the idea is if you have uncertainty in your initial and or boundary conditions, you can run the model many times with perturbations in this domain, and then that will give you a mapping to the forecast uncertainty. Sorry, didn't mean to do that. The ensemble mean can also offer an improvement over a single deterministic forecast, but there's also good reasons not to just collapse your ensemble to a mean value, because ensembles also enable probabilistic forecast techniques. And so this has been started to be implemented in CME prediction. So for example, this is a plot from Tanya Amerstorfer's paper on LEVO High, where they use an ensemble approach with the elliptical geometric modeling. And then this is a snapshot from Layla May's paper on using ensembles with WSA and Enlil cone model. But the trouble with, well, it's not trouble, the difficulty with doing ensembles in Enlil is that it's quite computationally expensive, and to run enough ensemble members to get a good handle on the uncertainty is computationally difficult. That's one of the issues. But in a 2017 or 2018 paper by Richard Harrison, he argued that it would be good to try and use heliospheric imager data to either weight or prune the ensemble members from some kind of time-dependent solar wind model like Enlil, or maybe even use data assimilation with them. And so that's what we've been doing recently. So we first tried this ensemble pruning and weighting, where we used HUXt for this. And so for the 4 case studies we had before, we said we could do an ensemble of HUXt runs, and then we can use the observations of the CME front to weight the ensemble members to try and see if that improves the ensemble prediction. And this is work we had published last September in AGU Advances. So how does that work? So for stereo A and stereo B, we have the heliospheric imager time elongation profiles. And then we did a 200-member ensemble of HUXt runs, shown here by the grey lines, where the black line is the unperturbed HUXt run with our best estimate of the CME's initial properties. And what you see is actually there's fairly close agreement between some of the ensemble members and the observed profiles, while some of them are wildly off. And so what we did is we computed the root mean square error between the time elongation profile and each of the ensemble members. And then we calculated a weight for each ensemble member as 1 over the root mean square error. And these plots here show how the arrival time error of each ensemble member is related to each ensemble member's weight. And so there is clearly useful information in the ensemble member weighting, in that the larger the ensemble member weight, the lower your arrival time error is likely to be. But there's also a lot of scatter in this, because essentially there's a lot of degeneracy in the time elongation profiles, because it's a projection of the CME's flank. You can get many different CME properties which give you very similar time elongation profiles. But what we found is that if you use those weights from the time elongation profile to weight the ensemble distribution, you do get an improvement in the estimated arrival time and the arrival time uncertainty. So weighting the distribution tends to move the distribution towards the observed arrival time and decreases the ensemble spread. So for the 4 events we studied, we found there was a roughly 20% improvement in the arrival time prediction and a 15% reduction in the arrival uncertainty. And so we thought that was quite a promising result. But again, we think we can do better than that. So we only consider the whole profile. And ideally, you would do something more sequential, where whenever you get a new observation, you update your forecast. And so that brings us to data assimilation. I'm running about 2 minutes late, 2 or 3 minutes late. So if you can bear with me just a little bit past 22. So data assimilation aims to produce the best estimate of the true state of a physical system through optimally combining physical models with observations. And to do this in a way that accounts for uncertainties in both the model and the observations. And how does it do this? It does it through a really diverse set of mathematical methods that I'm ill-placed to describe, as I'm not a mathematician. But the suitability of each approach does depend on the kind of physics you're trying to model, whether it's a fairly linear system or very non-linear, and also the nature of the observations. But the one that we've been experimenting with is a particle filter, which is one class, and in particular, sequential importance resampling. So the idea with sequential importance resampling is if you start off with an ensemble of model runs, so each particle is a model run, your model sends that particle forwards in time, use the model physics to work out the state at a later point, and then at some later time you get an observation, and then you compare each particle with that observation and compute a weight for each particle, which is dependent on how close the agreement is. Then you reinitialize that ensemble based on these weights, so that your updated ensemble should be a closer reflection to this observation, and then you send that forward in time. The advantages to this approach is that it's really very simple to implement, and it's a very general approach which is suited to non-linear work, and it also merges very naturally with ensemble modeling approaches. But a disadvantage is that if you've got a system with many degrees of freedom, you can very quickly need a very, very large number of particles, and it becomes very computationally expensive. But so we've been playing at doing this with HUXt. So the idea is we start off with an ensemble of HUXt runs, we send them forward in time, we compare them, we compare the model time elongation profile with an observed time elongation profile, and then we use that to reinitialize a new ensemble which is closer to the observations, and then you repeat that cycle as new observations come in. So how does it work for one particle? Well, so say we've stopped our model here at this point because we've got an observation. So we've got our model time elongation profile like this, and we've got an observation which is a slightly larger elongation. Well, to weight the ensemble member, we compute the likelihood of the observation given the model data. So we have to assume a likelihood function for each modeled elongation. And to do that, we use a Gaussian distribution. And so we essentially just look up the value of the Gaussian PDF at the observed elongation. And then the weight of each ensemble member is proportional to this likelihood. So if we have so this is a 50-member ensemble of HUXt runs. The truth run is shown by this black line. That is what we're trying to recreate. The 50 ensemble members are colored according to their likelihood of this observation here. So what you see is that the elongation profiles which are closer to this observation have a higher likelihood than the ones far away. So it works in a similar way to our root mean square error weighting, but this is more easily to do sequentially. And then after we've got those weightings, we reinitialize an ensemble, the ensemble at this new time step. So the black lines here show the initial ensemble members for the CME speed. And the black line is a kernel density estimate of this distribution of ensemble members. But when we weight these ensemble members by their likelihoods and recompute the kernel density estimate with those weighted ensemble members, we get this new distribution. And these red lines here are the new ensemble that's been resampled from this red line. And the dashed line is actually the truth value for the CME speed. So what we see is this weighting and resampling of the distribution has moved the ensemble closer to the true value. And so we repeat this cycle until you run out of observations, essentially. So I've got 2 more slides, I think. So to test this, you can do an observing system simulation experiment where you simulate a truth state in synthetic observations, and then you use that synthetic observations and truth with your sequential importance resampling scheme to see how well it does at retrieving the truth state. And you do this for many different random realizations. And so we've used 50-member HUXt ensembles with similar ensemble spreads to our earlier work. And we run this for 8 analysis steps out to a maximum tracked elongation of 30 degrees. And we assimilate observations every 3 hours. And we did this for 75 different backgrounds. And what you find is if you look at the distribution of the ensemble mean errors for the prior distribution, the one that hasn't been weighted, and the posterior that has been weighted by these 8 analysis steps, is it generally reduce the error in your ensemble forecast. And so you can see that generally the blue distributions have less spread than the gray distributions, which indicates that the posteriors have a tighter error distribution than the prior. In particular, it does quite well at the longitude, the width, and the speed, and the arrival time. But for latitude and CME thickness, there's less improvement. But this is perhaps not surprising because essentially the model is degenerate in latitude. Like you can't tell the difference between a 10-degree shift upwards or downwards because of the CME parameterization. And so to finish, although it's really promising that we seem to be able to reduce the errors on the ensemble forecast with this SIR scheme, there's still a lot of work to do because essentially that previous test I showed you collapses the ensemble to another deterministic prediction, and that loses some of the utility of the ensemble in that you can't really easily assess the uncertainty as well. So another thing you can do is to form rank histograms, talogram diagrams, which assess the performance of the ensemble. So So the idea is that the truth state should be statistically indistinguishable from the ensemble members. So for each individual run, the truth state should be equally likely to take any rank in that ensemble. So if you compute the rank of the truth in each ensemble member, and then you plot the distribution of those ranks, you would hope to see a uniform distribution. But unfortunately, you'll see that actually the truth state appears in the weighted, in the SIR scheme distribution at low ranks too frequently. And that is suggestive of the fact that our ensemble spread is too low. But so that's where I've got to with the SIR work. Essentially, we're very optimistic that with this reduced physics solar wind model with a particle filter scheme, we can make useful progress on improving CME arrival time predictions. I'm very sorry that I've overrun by 4 or 5 minutes, and I very gladly answer any questions anyone has.
Thank you, Luke. That was really interesting, really clear overview of the different approaches, and detailed as well. We do have a couple of questions which have come in, so I'll start off with Mike. His mic is broken, so I'll have to ask it for him. He says the HUXt ensemble comparisons with stereo HI. What were you varying in initial model conditions? He thinks was it background solar wind speed with Carrington longitude? Is that right?
No, so initially the ensembles just come from the uncertainty on the CME initial conditions. We varied the CME speed, longitude, width, latitude, and the CME's thickness. But Mike's right that there's also a lot of uncertainty in the background solar wind conditions. And so in future, we're also hoping to perturb those as well. But of course, every extra degree of freedom you add in inflates the necessary size of the ensemble. So we're currently working out the best way to go about doing that. Okay,
great. I hope that answered your question, Mike, but just respond in the chat if you have any follow-up. We'll move on to Martin. Oh, he said yes, exclamation marks. Martin says, nice talk. Is the idea for the data assimilation that you could continue to update arrival time estimates and uncertainties in real time when observing a new CME? How much data after first detection do you need before you start getting reasonable estimates?
So yeah, the idea is that the more data you assimilate, the better your forecast should get. But I mean, data assimilation isn't a panacea. It doesn't fix every problem. Your model should be performing fairly well without data assimilation before you start using it. It's not going to fix large systematic errors like that. So ideally, your model would have skill without the DA, and then the DA adds to that. And so you should have a useful forecast without it, and then the DA should make it better. How much you need to add to improve it is an open question. So far, I've only been doing these synthetic experiments. I need to get around to using some of the actual solar storm watch profiles to see how well it works. But I mean, I didn't have time to go into it here. There's a lot of free choices in how you set up, like the likelihood profile, the size of the ensemble, how you perturb the parameters to form the ensemble, and all of those things require tuning to make a system that works effectively. And at the minute, it's very early days. So there's lots of things to explore.
Okay, great, thank you. Martin says, okay, sounds very interesting. Gareth says thank you, and asks, is there a possibility of assimilating any in situ data from, for example, Parker?
Yes, so actually my colleague Matthew Lang focuses on doing data assimilation of in situ solar wind properties. And so you can take a slightly different approach. I don't understand it well enough, and can't really go into it right now, but as I said, there are different approaches to data assimilation, and Matt Lang has been developing one for assimilating the background solar wind observations from in situ monitors, and that works well. And so yeah, there's no reason you couldn't do that with Parker or Solar Orbiter. Yeah.
Okay, that's really interesting. By the way, if people want to ask their questions directly instead of having me read it out, just put your hand up and we'll let you unmute. So next question is from Mike Hapgood. Mike, did you want to just ask it directly?
I can. Can you hear me okay?
Yes.
Okay. Luke, thank you. That was lovely. I'm just, of course, thinking on what this implies for Lagrange, and as for keep making the point that Lagrange is a really important project. And it struck me that you're really showing that for L5 only observations, the physics is really important. And your geometric models, really, you would need at least both L5 and L4. So, again, it's saying, don't worry about geometric things, focus on physics. And I love these simple physics models that you can do big ensembles on.
Yeah, so I think that we will make more progress with physics-based models than we will further developing the geometric models, particularly for an L5 mission. I mean, it's something I want to look more in the work that we're preparing here. But I think there's more progress to be made with at least, I think you at least need time-dependent solar wind structure.
Makes a lot of sense. Thank you.
Thank you, Mike. That was a really interesting question. Next question is from James. James, did you want to unmute and ask your question?
Yeah, I mean, I was really thinking, you seem to imply that you were only using essentially the ecliptic plane angles for the measurements, whereas you might be able to distinguish latitude effects if you use the full 2D profile of the fronts, as we did with the geometrical Tappan-Howard model, which that mainly worked further out, high 2 region SME, but the same principle might apply.
Yeah, that's a really good point, James. That is something that would be worth looking at. So ideally, what we would like to do is, rather than identifying the elongation profile of the front, we would like to assimilate the actual HI data. If you had a forward model that you could couple your solar wind model to, you could come up with synthetic images and then do a direct comparison that would actually fold in that whole front profile. But yes, you're right that looking at the ecliptic only is limiting, and if we looked at the full front, there are other things you could possibly do. But again, that also makes things more complicated in the forecasting context, because it's more analysis of the imaging data you have to do when it comes in. So there's a balance to be struck between those things.
Yeah, I see the point. Yeah, what we did was to have basically a huge database of front edges for a particular family of geometries, and then minimize the residuals from, well, in principle, up to any number of different sets of observations from one spacecraft all the way up to, well, we never went beyond 3 because there were only ever three in operation simultaneously, SME and the 2 stereos. So that was always with high 2 though, rather than high 1, because the whole way that thing works is entirely reliant on the non-linearities. Thanks.
Yes. Yeah. Thank you, James.
Thank you. Are there any other questions? There's some follow-on comments in the chat, but I don't think they're actually questions. We've got a couple of minutes left, so please just pop them in the chat. In the meantime, I might go to a more basic question of my own, if that's okay. So you showed during the seminar how using techniques such as the Ensemble, Pruning, and the SIR scheme results in an error reduction. But I was just wondering whether that error reduction depends on or varies with different types or properties of CMEs.
Yeah, I think you're exactly right, Jasmine. So far, I've only been looking at that 1,000 kilometer per second CME in these simulations. I would expect all of the error distributions to be a function of the CME's initial initial speed in particular, but also longitude and width. Maybe less so the latitude and thickness. But yeah, it's going to scale. It's not going to be constant.
Okay, great. I was just thinking, because even though you mentioned before it's really important, and it's right, really important to model the typical CMEs because they can have like cumulative long-term effects. But in terms of like these really extreme events, I guess that's still also important to model, and whether these new approaches still result in error reduction for those really like extreme CMEs. We haven't had any more questions come up in the chat. So I guess we'll wrap up there because we've only got 2 minutes left of the meeting. But I just want to thank everyone who contributed to the really interesting discussion. And foremost, thank you, Luke, for that really interesting seminar. I learned a lot about CMEs and modeling them, so that was great. Thank you everyone who also attended. I hope you got something from it. Keep an eye out on the MIST mailing list. I'll be circulating information about the next month's seminar there, and you can always check the MIST website, and we've got the schedule for all upcoming seminars listed. So thank you everyone. Enjoy the rest of your day, and goodbye.